Okay, hi everyone. Welcome to this webinar on electromagnetic simulation in your browser. It's my pleasure to host and moderate this exciting event today. I'm Steve. I lead the application engineering team here in SimScale, and I'm joined by two presenters today. I'm joined by Jairi. Jairi is part of the application engineering team here in SimScale, and he's got experience in both CFD, FEA, and electromagnetics. He has a background in civil engineering, and he completed his master's studies in computational mechanics from TU Munich. And on the other side, we've got Oliver joining us today as well. Oliver is part of the product management team here in SimScale, and he has a diploma in electrical engineering, a PhD in mathematics, and he's a professor for computer science and electrical engineering in Munich, Regensburg, and he previously held management positions in simulation and software development. So who better to be leading our electromagnetics drive here at SimScale? A bit of housekeeping first. So all of you will remain muted throughout this webinar, but that doesn't mean that you can't engage with us. Please use the questions panel in GoToWebinar. You'll be able to ask questions as we go through. You may need to pull out the drop down underneath the questions panel in the GoToWebinar control panel, and you'll be able to talk to us in there. We'll answer your questions at the end of the session. Also, as we're going through, we'll ask a few poll questions. Get your opinions on a couple of things and find out what you're thinking. Okay, so let's get on with the main session. The agenda that we're going to go through today is we'll go through a very brief introduction to SimScale, and then I'll be handing over to Oliver to cover the need for electromagnetic simulation and the roadmap that we've got for this solver. And then we'll have a look at the overview of our current capabilities with Jairi. And Jairi will take us through an application that we're going to look at and a live demonstration of the software. And we'll finish up with any questions that we have. The whole session today will be about 45 minutes. And obviously, we'll make the recording available to all of the participants that have registered for this event in the coming days. So first of all, what is SimScale and what do we do? So SimScale provides a next generation cloud native engineering simulation platform. And how is this different from the traditional desktop tools? Well, SimScale is entirely cloud native. You don't need access to any hardware or software to access SimScale. All you need is a web browser. It's a true SaaS application, and you can access it from anywhere. We have one platform with broad physics capabilities. You can do flow, thermal, structural, and also now electromagnetic simulations. There's no change in the UI. As you'll see in the demo that Jairi runs later, everything is in one clean, simple UI. Also, thanks to the fact that we are based in the cloud, it opens up possibilities for real-time collaboration and real-time support. There's no need to transfer large files if you want to collaborate across geographical boundaries. If you have one engineer in North America and one engineer in Europe, they can just log in simultaneously and access the same data from the cloud. There's no need to transfer huge terabyte-sized files to work on the same big simulations. Also, our support is very different to a traditional tool. There's no support tickets. You just use the chat functionality and you immediately have access to simulation experts such as Jairi to answer your questions and help you with your simulation. We typically respond within a few minutes in business hours for Europe and North America. Also, as with many companies these days, SimScale is AI powered. We have some really powerful tools using AI to make your life easier in SimScale. We have a very accurate estimation of the resources required to run your simulation. So before you set off a simulation, we use the thousands of simulations that we've got to estimate how long your simulation will take. And we're also releasing AI predictive physics capabilities so that you can predict what your simulation is going to be based on a machine learning algorithm that you have built in. And with SimScale, you can simulate at any scale. This has multiple meanings. You can scale easily within your organization from one engineer up to hundreds of engineers without having to have expensive workstations, without having to install software. Everyone can just access it from their browsers. Also, you can scale the number of simulations that you run. So today, maybe I just want to run a simple FEA simulation. But tomorrow, maybe I want to run a design study of an electromagnetics case with 3,000 simulations. I don't need to contact SimScale and say, can I switch on an HPC license, or can I access more computing power? It's all available to me at my fingertips immediately when I need it. So more specifically around the physics that we have in SimScale, SimScale provides a broad set of physics on one cloud-native platform. And I'm really excited today by the fact that we're actually implementing a new physics. So before today, we had flow, structural, thermal simulations available in SimScale. But now we've also introduced electromagnetic simulation. This is thanks to our collaboration with EMWorks. And the capabilities that we're going to present to you today are going to be released in the coming days. However, if you would like access to this electromagnetic solver now, please message us in the chat or follow up with us after this webinar or after you've watched the recording. And we'd be very happy to enable this capability for you immediately and get you working with our electromagnetics solver in SimScale. Okay, so that's all from me for a brief introduction, and I'll hand over to Oliver now to take you through a bit more details of what we're doing. Thanks.
Thank you, Steve. Yes, hello. Let me just mention a few reasons why you should dive into electromagnetics. And so, for instance, if you're already an electrical engineer and you are already designing electromagnetic devices, the first reason is quite obvious. So you want to develop your electromagnetic devices or systems efficiently. And for doing that, you're using simulation usually, as for other applications as well. So what you can do, so the functionality of many products today is based on electromagnetic phenomena. And if you want to do an efficient development, process, you usually do things like front loading. That means you spend more time at the beginning of development using simulation and putting less efforts in building prototypes. So that's a well-known established method today. And of course, this is one reason to use electromagnetic simulation, and also one reason for us to provide this. And of course, you can use electromagnetic simulation not only to make a more efficient development, you can use it to understand an electromagnetic phenomena in the same way as you use thermal or CFD simulations for understanding phenomena and build even better products or understand new ideas. But even if you're not an electrical engineer, and even if you're not designing electromagnetic devices so far, there are two more reasons why you should start considering diving into electromagnetics and maybe starting using simulation as well. The first reason is the second reason to deal with electromagnetics is the number of electromagnetic applications is increasing. So one reason, I think you already see that cars that formerly has not been based on electromagnetics, they are now using electrics to drive, and so that's one reason. And there are also helicopters, and there are already other devices that are now based on electromagnetics. Even pure mechanical components. When you was, for example, in former times, when you want to open the window in your car, you have done this manually doing a mechanical, using some mechanics. Today, you just press a button. There are some electric motors, there are actuators that are now working. So the number of electromagnetic applications is increasing. And there's the third reason. If you model devices, they are usually smart devices, and they are not just a device that are based on one physical domain. They're usually cyber physical systems. What does it mean? So if you develop smart devices, they have some software, some intelligence included, and of course also some electronics. So if you want to develop this efficiently, you have to model a system that consists of mechanics, heat transfer, electromagnetics, and software. So even if you're based, or many are used to do mechanical simulations or mechanical designs, in future, the likelihood that you also have to do something to do with electromagnetics will increase. And that could be one reason to start now doing some electromagnetic simulation and build up your skills in doing that. And to support all of these things, we make electromagnetics available now in your browser, and it's easy to start with it. Let me show a rough roadmap how we do this and why we start with our first applications. So our roadmap looks like this. So we start with providing magnetostatic simulation. Magnetostatics means there is no time dependence in your fields, and the focus is on magnetic fields. And for instance, we can excite such things with defining some coils where current or voltage is applied. And you can excite it by permanent magnets. And applications you can model for instance, actuators, solenoids, sensors, clutches, motors, or you can also extract inductances from your device to do a further simulation on circuit level. This is currently available, and Kyrie will show you in detail what you can do with it now. Currently, we are developing the next level, which will be the time harmonic magnetics, sometimes also known as AC magnetics, and also known as eddy current model. So what is solved is the so-called eddy current model, which is a simplification of Maxwell equations, which describes magnetic effects that are time dependent, where the induction effect is an important effect. Typical applications are transformers, sensors, shielding, induction heating, and many further. The next step on our roadmap will then be also time-dependent magnetics, but generally time-dependent magnetic problems. We call it time domain magnetics, sometimes called transient magnetics. And again, it's the same low frequency approximation of Maxwell equations, which is called the eddy current model, but now with general time dependency. And this solver will be very important for simulating motors, generators, transient processes like switching, and many others. So after having covered the magnetic side of electromagnetics world, we then start with supporting the electric field in more detail. So we start with the classical electrostatics, where we solve the low frequency or the static equations that are important for instance, for calculating insulation coordination, determining capacitances, and you can also simulate a lot of different things like sensors that are based on the electric field, and many further things. Then we complete this by DC conduction. That means while the electric field electrostatics covers the field outside the conductors and insulators, the DC conduction problem solves the electric field inside the conductors in the case of DC, and which is, for instance, for example, it's important for calculating bus bars, joule heating, and many different applications, and determining resistances based on geometry. Finally, we will start to also provide a solver in high frequency, and which will solve the time harmonic Maxwell equations, which is important if you want to model antennas, microwave guides, or filters, and so many other high frequency applications. And then, depending on our experience, what you would like to see in more detail, or where there's a high demand, this will determine how we go on afterwards. For instance, we could provide low frequency electrostatic simulations, so low frequency electrics, or other solvers. That depends on the experience that you will have and the demand from you. And I just want to mention the technology we use and we integrate in our platform is based on a well-established technology by EMWorks, which is a well-established and proven technology and used by many, many customers for many years. And so we have a very established and technology inside, and we are very proud to have a very good collaboration with EMWorks. Yes, so now let's look in more detail what is now available. We are just starting with magnetostatics, and Kyrie will show you in detail what you can do with it. Thank you.
Excellent. Thanks, Oliver. So over to you now, Kyrie.
Perfect. Thanks, Steve. Thanks, Oliver, for the nice introduction, and a warm welcome from my side to everyone attending today. Thank you for that. Right now, what we are going to be looking at is we're going to look at an overview of the magnetostatic solver. So what is incorporated inside it? What can you do? What can you simulate? And then we're going to look at a live case study very quickly so that we can see everything live in action. Now, on this slide, we have an overview of the current capabilities. So this just shows a few examples among the many examples that we have simulated already with the current development of the magnetostatic solver. And we see here bullet points of some of the available capabilities inside. So of course, what can you expect from such a magnetostatic solver? You would expect obtaining information on the magnetic field intensity H, the magnetic flux density B, the current density J. You can of course set up nonlinear and linear magnetic properties. You can import your own BH curves. The excitation of the magnetic field, of course, can either be coil driven. So the coil could be excited by either a current or a voltage, or you could excite it directly via a permanent magnet too. And as results, what you can expect is to obtain information on inductance matrices, coil resistances, forces, torques, 3D fields, and so on. Among those applications that I'm showing on the screen, what we will look at in particular is the toothed holding brake. Now, those toothed magnetic holding brakes are very similar in application to what's called an on-power holding brake. So the only difference is that with the toothed magnetic holding brake, you can achieve a much higher static torque due to the mechanical interlocking between the driven and the driving teeth of the system. And those can be used in various applications, such as, for example, elevators, conveyor systems, robotics. So the scale of where they can be used can really be different depending on what application area it should suit to. And the main goal of those brakes is really to ensure a precise stopping and holding of the motion at a particular instant. With the magnetostatic analysis, the objective today is to really look at how we can optimize the magnetic field distribution, meaning that we're going to look at the magnetic field distribution, the magnetic circuit, and most importantly, we want to understand what is the overall braking force generated from the simulation. Because then we can take this braking force and put it into a structural analysis in SimScale, and then we can investigate what is the structural integrity and the interlocking mechanism between those two. We can now take a look quickly at a quick simulation synopsis. So I have ran two different cases. One of them represents a standard toothing, while the other represents a sawtoothing. For both of the cases, they've been designed with a 2-degree misalignment of the teeth. So for example, between the stator teeth and the armature teeth, there is a 2-degree misalignment, which is something that could really happen inside the application as well. We want to investigate what is the interlocking mechanism between those two. And of course, the first step to do that is to run a magnetostatic simulation so that we can estimate the forces needed. For the particular materials used, so we have the coil. Now we're looking at a section view of this particular tooth holding brake. So we have the coil, which is made of copper, the stator housing made of a high permeability material such as iron. We have our input and output drives made of brass, and we have essentially finally the armature, which contains the teeth for the interlocking made of typical steel. Both of the stator housing and the armature tooth section are both made basically set up in the simulation with a BH curve material so that we can actually investigate any possible saturation effects that could occur and really model the formation of the magnetic field accurately inside the magnetic circuit of this system. When we talk about coils, coils can be set up in two ways. So either voltage driven or current driven, depending on how the application is set up or the system is set up. In this case, I have ran a parametric simulation for a current driven coil. And in this parametric simulation, I'm investigating multiple different, basically multiple different application scenarios or operating conditions, in other words, right? Where for the two different models that I've simulated, the sawtooth and the standard toothing, in total, I've run 22 parallel simulations in 72 minutes. So for each one of them, 11 different operating points were investigated. And the time it takes, that's the nice thing about essentially utilizing the power of the cloud, where you essentially, if you have one simulation that's going to take, let's say 70 or 50 minutes, that's the same time that 60 or 100 or even 1,000 simulations is going to take, because you have access to an unlimited parallelization capabilities with SimScale. Now that is clear. Let's jump in now and see the SimScale platform live in action, and then we can jump back to the results and look at some, finalize with the results and question and Q&A session. Cool. So now I'll just switch my tabs directly to SimScale, and where we are at the moment is inside the SimScale dashboard. So when you first log in into SimScale via your username and account, you land inside your dashboard, and your dashboard is basically the system that allows you to manage all of your simulation projects into different folders. You can share each project with your colleagues. It's like a management system for all of the data that you have. The cool thing about SimScale as well is that you never have to worry about any storage data. So basically, you have unlimited storage with SimScale. You can have as many projects as you want, and so on. Now we can take a look at the tooth holding magnetic brake, and we'll start first by looking at the results of it. So now I'm inside the SimScale platform, the SimScale workbench, and we're looking at the results. The first thing that you may notice is that SimScale is completely cloud native, as had been already explained. So this means that you do not have to worry as well about any hardware investments. And this topic becomes quite important as well in companies and organizations where scaling up the use of simulations is becoming now more the norm in the industry. We know that simulations in general can sometimes be quite expensive or demanding for the hardware, and you need to invest in a proper workstations, even in a proper IT management system to manage all of those workstations together for such like a setup, or basically an R&D setup in the company. With SimScale, this cost of investing in hardware is completely eliminated because everything is directly powered in the cloud. Now, let's take a look at the magnetic circuit generated from this simulation. So we see over here, we have the coil that's generating the magnetic field. You see how the magnetic field essentially is forming a closed circuit between the armature and the actual stator housing around the coil. What we would like to also make sure here and investigate in detail in different applications is that from here we see that the teeth of the armature, how they are magnetized. Now this is set up with a nonlinear magnetic permeability, so we can also investigate any saturation effects that could affect the total force generated and so on. Inside the post processor, of course, you can also investigate the current density. The flux density is what we are looking at the moment, and the magnetic field intensity H. I would suggest that, for example, perhaps in a later webinar, we can look at a particular example, maybe this, or if you have any other ideas that you would like us to do in more detail, a complete design workflow, we can also do that, and we can discuss a particular case more in depth. For now, my goal is to really just to make sure to deliver a message of what is available at the moment inside SimScale and how we can set up such simulations. So now that we have taken a look at the results, let's jump over to the actual simulation setup and take a look at how we can set up one of those. So what we have over here is the same tooth magnetic holding brake, but now inside an air volume, because the magnetic field essentially requires that air volume, so that it lives inside it. And what we want to do, the first step, is to import a CAD model. Now, we do support in SimScale almost all native CAD formats. Those could be Parasolid, SolidWorks, Inventor, etc., etc. Once you import your CAD model, you can go ahead and create a simulation. And as Steve already mentioned, SimScale is a broad physics simulation, so you can run either flow, structural, and now recently electromagnetics simulations. When you create an electromagnetic simulation, you would be prompted with what we call the simulation tree. And this is your guide in setting up the simulation. The idea behind it, you start from top to bottom. Everything that's blue and red indicates that some action needs to be taken there. And the same simulation tree layout is consistent with all of the other physics that we have. So for example, if you're setting up an electromagnetic simulation, more or less the simulation UI should be similar for the other one so that you don't be confused between all of the other analysis types. Now, for the interest of time, I will take you through the setup of one of the simulations that we had here already. And we can start by looking at some of the materials. Let me have the air volume. We can look at the setup, for example, of the armature material, so the typical steel material that we have over here. So for the material behavior, you can either define a soft magnetic or a permanent magnet. In this case, we have a soft magnetic material with a nonlinear magnetic permeability. So we have the BH curve imported. You can, of course, just drag and drop your CSV files to apply your BH curves, and you do also get access to a default material library with SimScale that provides different values essentially for the relative magnetic permeability for standard materials. If you do have typical materials that you use in your organization and you would like to have those saved in your SimScale library, then that is of course possible. We can import your own company materials, which you can then use and access across all of the other projects for all the team members in your organization that uses SimScale. Now, the second step after defining the materials is to define the coil. So to define the coil, let's just isolate it so that we can look at it. There are two different ways to define a coil. So either depends on the coil type that you have. So you can either have an open coil or a closed coil. In this case, we have a closed coil where the topology is actually closed on itself. And to define that, we need to define an internal port to define essentially an internal phase that the current goes from one direction to the other and loops around. So for this case, we can just essentially hide one of those faces and choose the internal face inside, and that would be your internal port. So it's important to split the coil into two parts when you want to have a closed coil definition. For a closed coil as well, you get different settings than a solid coil. So for example, here we need to define the number of turns, the wire diameter, and the excitation. So whether it's going to be current or voltage driven, as already mentioned. Something that's you get with a cloud native solution is the ability to run parametric simulation right away on different machines directly on the cloud. So here we have a parametric simulation setup for 12 different inputs of the current, so different operating conditions. And the same is done for the sawtooth simulation as well. Now, as that is clear, finally, what we need to do is really just to define what additional results we would like to get from the simulation. So we can request to calculate the inductances, and we can request as well to calculate the forces on the armature ring. That's essentially what's going to bring the braking force into the stator housing and then generate the static torque needed for the braking mechanism. Now, as that is done, I could go ahead right now and run this simulation right away. So what I will be doing is I'm going to be running an experiment, and I will be running now 12 different simulations in parallel at the same time. As we see over here, each one of those simulations now fired to a different machine on the cloud, and the time it takes for one of them to finish at the same time takes for all of those 12 to finish. Now, the main output that I was looking for from this simulation is the total braking force generated. And that's something that I could investigate for each one of the runs that I had. So I see that I have a total force of around 4 kilonewtons generated for this particular design for the particular operating conditions. The next step now is to go ahead and set up a finite element simulation, which we will not look at into detail in this webinar. I'll just take you through a little bit the setup. So we have here a quarter model to optimize the simulation efficiency. And all I need to do is just apply the 4 kilonewton force, of course, divided by 4, because we're simulating a quarter model, to the simulation. And then I can go ahead and run this and investigate the overall results. And of course, the interlocking mechanism, that's something that we are also looking for. Right? So now I have 2 simulations running, both for the electromagnetics and the finite element simulations. Sounds good. Now, something that I also want to emphasize as well is that with SimScale, you should remember that you are never alone. And I say it in this way because it's truly like that. You always have access to the in-product chat that's available. So you can write us any message, hi, I need help in X and Y. And X and Y can literally be anything. For example, you might be asking us, hey, can I simulate this physics? Or how can I set up my boundary conditions? Can you help me with post-processing? And so on and so on. Behind the scenes, we have the SimScale engineers who are very experienced in all of those fields that we have covered today. And their main goal is to really make sure that you end up getting a successful outcome from your simulations. And I would really encourage you to make use of the in-product chat. Now, let's jump in back to the slides and summarize the results very quickly and jump in back to the Q&A session. Cool. So here in the slides, what we have over here is both the total, essentially the magnetic circuit screenshots from both the sawtooth and the standard toothing. And then below, we see the animation of the actual interlocking mechanism between those two. Now, as I mentioned at the beginning, there was a 2-degree misalignment in the design between these two. For the standard toothing, we see that because of this misalignment, we have high stresses being generated at the corners that might make this a suboptimal design for a particular application. Such a problem is mitigated with the sawtoothing, which allows for a more area for the interlocking. So this allows for a better torque interlocking mechanism between those two. And with this, I would like to conclude this technical demonstration, and now we can jump into the Q&A session and take some of your questions.
Brilliant. Thank you for that, Harry and Oliver. I really like that demonstration because I think it really shows what's possible with SimScale now that there's multiple physics available, including the electromagnetics. You can really find out what the force would be and evaluate that in a structural analysis. Obviously, we didn't have time to cover everything today because you could also use Joule heating in a thermal analysis to have a look at how those electric currents heat up the whole assembly, and you could analyze the thermal properties as well. So it really does enable multiple physics for your designs. So please send in any more questions that you've got. We've got quite a few questions to get through, but we do have space for a bit more. If you have anything that you would like to ask Oliver and Harry, we'd be very happy to cover that. So there's one that came in. I think this is for you, Oliver. Someone's asking about the future development of DC conduction and when that will be available, when DC conduction is likely to be available from the roadmap. Oh, sorry, Oliver, we don't hear you.
So in the electromagnetic solver, it's most likely available at the end of next year latest, so it will be very, very soon available. If you are looking for DC conduction in combination with Joule heating, for instance, there's already some solution available. If you look on our electronics cooling applications simulation, there is already some functionality. If you want to do thermal simulation, so combining heat transfer via fluid plus heat transfer via conduction, and combining these, for instance, for simulating the thermal behavior of a complete housing, including electronics. There is already a feature available that allows calculating DC conduction, which automatically gets the the heat generated by the ohmic losses, and which then is a source, the thermal source for the thermal calculation. So if this is the application you have in mind, it makes sense to have already now a closer look to it. If you have other reasons, if you want to combine it with other applications than joule heating, it makes sense to wait a few months until it will be available in the electromagnetic solver itself.
Great, thanks, Oliver. Great answer to that. Yeah, so we've got a couple of different questions come in on the same topic here. So one person has said, if I want to run a DOE study, I may need to run many simulations with different parameters. Do I need a special license to run all of these simulations in parallel? And how many simulations can I run in parallel? We've also got another question from someone else saying, do you have capability to parameterize the setup and the geometry? And how many can I run in parallel? And another question saying, what's the maximum number of simulations that I can run in parallel in SimScale electromagnetic? So yeah, popular topic. Jairi, how many simulations can you run in parallel?
It is unlimited, really. So basically, we have many different customers who make use as well. We have an API, so you can write your own scripts and parameterize different applications to different ways. So you can even link them with other applications as well to have a proper optimization loop in place, and you can really run as many simulations as needed. So there is absolutely no limit on that. And the only limit is basically for you just to start working with that, start developing the code. That's essentially the only needs that needs to be achieved for that to happen. But from our side, there is absolutely no limit. And the question on the licensing is that do you need a special license to achieve that? No, that's not needed. Essentially, with a standard SimScale license, you would also be able to run as many simulations as you want for all of the different physics that would be included in your license subscription.
Yeah, exactly. Great answer. The parallelization is unlimited and no special license required. So perfect. Someone else has asked about a specific type of simulation that they would like to run. They've asked if it's possible to design a Faraday cage to reduce the magnetic field to prevent interference with other pieces of electronic equipment. So Oliver, I think that's a question for you. Is it possible to design a Faraday cage with SimScale?
Well, generally now, currently, we only have support to magnetostatic, so that's the very first step. So Faraday cage usually is based on conductivity of the electric field, so to have or reduced electric field inside the cage. So this will be supported by our future solvers. What you can do now is magnetic shielding. So if you're interested in shielding static magnetic fields, which is not really easy in practical cases, then you can calculate magnetic shielding. That's what now possible if you want to have traditional Faraday cages, or more generally having shielding effects for time varying or static electric fields or time varying electromagnetic fields. Then you have to, unfortunately, you have to wait for our next level of development when we will make the next solvers available. That's the current state.
Okay, great. Thanks, Oliver. There's a more general question about material properties. So someone has asked if they can import their own customized material library into their SimScale project. So I can happily take this one. So yes, you can import your own material properties. When Jairi set up the material for the stator, you can edit the properties directly in there. So you can edit the example materials that we provide to add in your own properties. But also you can upload your own materials into SimScale with SimScale support. So both of those things are possible, yes. I've got a question to put to the audience as well. Would anybody here today who hasn't already mentioned that they would like to have access to this solver like to access it? If you would, drop us another message and we'll happily follow up with you after this session and enable your access before the full release. Okay, there's quite a few questions coming in. I fear we're not going to have time to answer all of these, but let's have a look at another one. So, is it possible to simulate eddy currents and proximity effects in conductors? And someone else has asked a very similar question. Is it possible to simulate eddy currents on the AC cable shielding and check I2R heating? So yeah, great question. Who would like to take that, Harry or Oliver?
Oh, you can Harry, if it's okay, you can comment on this.
Yeah, please.
Yeah, so,
please, Oliver. Yes.
Yeah, so the eddy current effect and the skin effect, as well as the proximity effect, are based on induction effects. Yes, so the Faraday's law of induction is a crucial phenomenon here, and this is not part of magnetostatics. So this is time variant field. It could be time harmonics, but it's time dependent. And so this will be supported by the solver, which is now in development, and it would be available very soon. And you could use our time harmonic magnetic solver if you have time harmonic eddy current problems to solve and to calculate skin effect and all these things. This will be possible with this solver coming soon. And if you will have general time-dependent problems or nonlinear materials included, then this would be possible with our time domain magnetic solver, which will be available after the time harmonic one. So short answer, not with magnetostatics, but with the next level of development, it will be available. So it would be great if you would just leave your contact and we could contact you as soon as it will be available, which would be quite soon.
Perfect. And yeah, just a note, because we're not going to get to all the questions, there's a lot coming in. We do have your details if you've asked a question and we haven't had time to get back to you. Don't worry, we will follow up with a response to your question. We will send the recording in the coming days and we'll follow up if there's any unanswered questions as well. Something I think is worth mentioning, we've got a few questions about the roadmap, and the roadmap is not entirely fixed. We're quite happy to adjust things to requirements of our customers, and we're taking feedback on board. As we implement this electromagnetic solver, the customers that we have and the feedback that they give will definitely influence the priorities that we make. We always take our customers' feedback into account when we manage what we're going to develop at SimScale and how the roadmap is prioritized. So please do join up, try out this new capability and have a discussion with us so that you can influence what comes next. Okay, so yeah, on to the next slide, I think, Harry, for next actions. So thank you very much to Oliver and Harry for that brilliant introduction to what's coming and what's available. So the next steps are, it's really over to you, over to the audience, and those of you who are watching the recording as well. This, of course, applies to you. You can have a demo of this capability. You can speak directly with us. All you need to do is contact us. You can contact sales@simscale.com or simply visit simscale.com and request a demo or sign up, and we'll get back to you. We normally respond within 1 business day, and an application engineer will be able to join a call with you and demonstrate the capabilities and find out how SimScale can help you innovate faster. So thank you very much to everyone who's joined. Unfortunately, we're out of time now, but we'll see you next time. Thanks. Bye.
Thank you for joining.
Thank you. Goodbye.